Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi. Very good afternoon. Very good morning. Can you hear me, class?
Can.
Right. Good. Okay. So today kita go for online. So I will conduct this class online. But frankly speaking, class online is I'm not keen on online. Start with maybe I have kind of difficulties to explain to you more for this course. All right, class, for today, kita go for the new topic. I thought I want to discuss about your project. You proceed with your project. Do not postpone your project. Actually, you already have the group members. Later, we will discuss on the WhatsApp. And for today, I will go for the new topics. This new topic actually is not, it will be in your test too. What topics that will be covered in your test too? I've already done a lecture. I already explain to you all the topics for the test 2, which is about the gear bending strength, gear surface strength, and also the bearings, and also the Mitsubishi V-belts. So that's all for your test 2. We have 3 questions. The first question will be gear strength. Normally it will be on bending. Sometimes maybe you go for surface, make sure you prepare for it. Second question will be on the bearings. Make sure you prepare. How do we do the bearing selection? And the third question of your test 2 will be Mitsubishi belt. I think that is kind of it's not a difficult test to compare with test 1. Right? So that's all for your test 2. But this one, another topic I need to teach you is about selection of bolts, right? Bolts and also welding. Welding will be our next meeting next week. Right after the AIG, when we next week also we will meet on. I don't think so. We'll meet on Monday. We'll meet Tuesday. All right. Okay. Then after next week I will go for welding. Today I will go for bolt selection. Okay, a little bit online. I kind of not used to it because. All right. So what bolt selection? I think I already attached to you guys. Ada I attach the notes in WhatsApp. Bolts. Ada tak class? Hello class, can you hear me? Sometimes I need to interrupt. Sometimes during previously when I'm doing conduct online, I've been talking for hours. Actually, my class cannot hear me. Kan like this. Boleh dengar saya kan? I keep interrupting every 5 minutes.
Boleh.
Okay, I think I already share you in the WhatsApp. What about both in PowerPoint. Ada tak class? You have it. Open the notes. There, right? Okay. All right. If you look there, if I share you, it's about bolt. Okay. Normally, before bolt is actually okay. Bolt will not be in your test 2, but it will be in your minor project. Actually, you have major project, and your minor project I've not give you yet the title. Minor project is the same group of your major project. Previous semester, I gave student the minor project is about later we'll discuss, or maybe sometime I will integrate that bolt and welding into your what your major project title is about coconut shell crushing machine. Maybe your bracket to hold the motor, then you will use bolt connection, and maybe about the sustain your system, your power transmission, and your shaft, or maybe your hopper, your design. You have a feeder. You don't have to design the feeder. Actually, you can just simply draw in SolidWorks a feeder shape. Maybe I integrate to hold the feeder. Maybe use welding to bracket to hold the feeder. You are not designing the feeder. Maybe that is kind of if I want to integrate the bolt and welding into your major project. But previously, I give separate title for the bolt and welding. Later, we will discuss for it. All right, today we will go for bolt. You can see my video class. I'm sharing the video. Okay, if you look, it's about bolt. Bolt selection. Bolt is boleh dengar saya kerana pernah saya cakap sedikit. Boleh dengar Kelas, line okay? Kelas, line okay?
Boleh.
Bolt selection. Okay, bolt selection. We do it. Bolt is fastening. It's a fastener. You know, bolt is a fastener. Fastener yang non-permanent joint. You already learned this in engineering. Non-permanent joint, which is fastener like bolt, screw. This we can assemble, disassemble bolts together with nuts. Okay, bolts, we focus on bolt. We are not focused on nut. Actually, bolt will be together with nut. It's non-permanent. It means we can attach and detach. We have two plates, two brackets attached to each other by bolts. Okay, bolt, we are not designing bolt. We are selecting bolt. Like bearing, you are selecting bearing. Like V-belt, you are selecting V-belt because bolt is a standard component. They have a supplier for bolts, right? So it's matter of choosing the right bolts. For example, same goes like bearing, choosing the right bearings, choosing the right V-belt. Same go for bolt. Bolt is when we go for bolt, it's just when you look at front view, we have hexagonal head, and we have a long like this. So this is actually the bolt length. The bolt length is here, not from the end of second. That will be your bolt length. And here, one part of the bolt we have thread. I make a double line. This is what you learn practice from your engine drawing. So this will be the thread. So one area we have thread length. This one we have thread length. Thread length is the length of the bolt where you have the length, and this one is a shank length. Shank is the part that we don't have bolt, because bolt is a non-permanent joint. It's a standard component. When we assemble bolt, it means when, for example, if I draw that, like for example, the bolt is meant for, okay, it's a cross-section view. Okay, you want to join the bolt. Guys, video I keep interacting, guys. Video okay? Boleh nampak Plus?
Boleh,
Can you hear
boleh.
me? Okay,
Boleh.
saya kena cakap tanya, awak pun fed up tanya pasal nanti saya bercakap panjang-panjang, rupanya line tak ada, penat je. Right. This for cross-section view, we have two plate or two bracket. You want to join each other, so you will be jointed, fastening by bolt. Bolt normally, if you have bolt, sometimes bolt, if you look, bolt is be clamped, locked by the nut. Normally, guys, kita ada washer, tapi we don't actually washer. You know, washer is a ring, right? A ring. To provide the uniform loading, right? Clamp, secure, to secure the nut. Without the washer, nanti the nut by easily. So this is a nut, right? So this is a nut, clamp by the nut. So this is a bolt. Bolt, when you join it, this is a bolt. And so the bolt is sometimes the type, when you want to select the bolt, you have to really identify what type is loading occurring on the bolt. What type of loading occurring on the bolt? For example, you have a cross-section view of two metal plate, you join it together by bolt. Okay, bolt, normally when you clamp it, other parts, if you look at my video, other parts, this is the threaded part, right? Threaded part. When I draw it, is threaded part, right? This is a threaded part, right? So it means that between these two plates, there is a threaded part. That's why it really clamps it, right? Okay. When you bolt, normally what type of forces apply on the bolt? What type of forces apply on the bolt? We might have tension for axial force. We might have normal stress, normal force, or produce normal stress. We might have axial stress. We might have a V. This V is shearing. What it means? Shearing the bolt. So it depends on what type of loading applied on the bolt. It might have tension load. When tension load applied on the bolt, it will produce axial stress or normal stress on the bolt. If the type of loading applied on the bolt is kind of like shearing, it's not tension. With what's occurring here at the section, it might kind of like a shear cutting on the bolt. So that will be a shear stress. For example, like axial stress, F here is a force over the area of the bolt. Shear, normally what you know, shear is shear stress. Shear stress, where shear stress, tau is V over the area. Kelas, okay, kelas, line, kelas, ada bunyi line, okay?
Okay, sikit.
Alright. So we might have axial, kalau normal force, we have axial stress, so cross-section of the bolt. Cross-section of the bolt is area throat. It's not, normally bolt, the bolt, for example, you use bolt N10 kali 1.2. So this is what I learned from engine drawing, N10. So the diameter of the, why is 10? 10 is the diameter of the bolt. So you mean this hexagon head. So this is bolt length. So part of it we have thread length. Okay, we have thread. We have thread part of it. Okay, this is the diameter of diameter 10 stem or diameter. So it means the major diameter of the thread. It means from the peak to the peak, right? Not the minor. The 10 stem from 1.2 is a pitch. Okay, to focus on the size of the bolt is the major diameter of the bolt. For example, like axial stress force over cross section of this. You take the diameter is 10, right? So you might take pi over 4, 10 square, right? Pi over 4, the square, that's the area of the bolt. But we don't take 10. We have a table to, because that is the reason for normal stress force over cross section of the bolt. Of course, we will take the major diameter, but we don't take the major diameter is 10. We don't take 10. Actually, we go for area to, because why? Both when it is jointing together, because we clamp with nut, it means both have initial tension inside it. So it means that's why from the table, the engineers already put the area to area to mean that we don't go for pi over 4, 10 square. Okay, but for the shear stress, if your stress occurring shear, when shear you have a cutting section, shear plane, right? Shear is cutting, it's like it's a shearing. So we go for V over A. What's the shear load and what's the cross section of the bolt? But cross section of the bolt, it depends on what. If your shank, because this is two plate, you have shearing. So the area of shear is this line. If you look like this line is shearing, right? So if this at this section, the thread is not there, the thread is stuck only here. So it means at the shank length, it's not on the track area, on the shank, it means on the major diameter. So there will be the area shear. So tau is B over the area of shear. Shear depends on which one. Be careful about it. Normally, both the shearing happen on the non-threaded part. Be careful. Normally, that's the way the bolt join to the division. So that type of bolt. Okay. We have two categories of stresses when we selecting bolt. Okay, we have primary load. As I mentioned to you, we have primary load and we have secondary load. Okay, primary load and secondary load. Where primary load we have just now the primary load is axial stress, and we have axial stress force over area load, and we have torsional stress V over area. That will be this is a primary load because of the tension and also shear stress. Secondary load is due to torsion and also due to moment, due to bending moment of the bolt. Okay, this is just a briefing. Let me share you the PowerPoint option. If I share you the PowerPoint. Okay, boleh nampak my PowerPoint class? Class PowerPoint, can you see? Right. So this is PowerPoint. If you look, so introduction of bolt. So this is our beam where we have a bolt connection. This kind of, if you focus a cantilever beam, we have a vertical beam like that. So the top is a plan view, and this one bottom is a front view. So we have a uniform load acting on the beam. Then we have a joint, fixed joint. Bolt is a fixed joint. We have like this. So this is a zoom version. We have 4 bolts we want to put at each joint. So if the fixed connection. Okay. All right. Right. So if I go for, okay, this I mentioned to you is now the nomenclature of the bolt. We have shank length. Okay, you can see my point. Tell me again. Kalau apa you cannot hear me, just interrupt me. All right. Shank length, and we have a threaded length. All right. So we have, okay, axial load. Okay, axial load both with possible fatigue crack, correct? Crack location. When we have both, we have axial loading. 50% of fastener fatigue failure under the head. Okay, under the head, this is 50%. 20% at the thread round rod. What is the thread round rod? Thread round rod is, if I show you, thread round rod is here, where area where the margin between the threaded and non-threaded. That B2 thread round rod. Thread round rod. See this where there is a thread. There is a thread, and start from B is a thread. The margin where is we don't have thread. Thread round rod at B. 20% always occurring when we have axial load acting on the bolt. But 65%, can you see that 65% at the shank? Where is shank class? Shank mana? Are you listening?
Position C.
A to B. No, that's not Shank. Shank, this is Shank. Now I show you. Shank, mana Shank? This board ni opposite, this is reverse direction. Shank here, non-threaded. The length, itu Shank. So Shank this one, so this is Shank. From here to here, the non-threaded. So I mean, we focus on the Shank board. Normally board when we join, like I show you just now, it's not actually on the threaded part. It focus on the Shank. The major diameter of the board, still focus on the 65% of the feather. All right? Between A and B, that's the Shank leg. Okay, this area, this area, this is a Shank, right? So you focus on that. Okay, the terminology major, this one already explained to you in engine drawing, major diameter. What is the pitch? You must follow pitch of what? Pitch, upper pitch. What is pitch? Pitch apa? From the peak to peak end, from the peak to peak distance of the thread, that is we call pitch, right? All right. This is a nomenclature of the board, major diameter, minor diameter. So we have a pitch, we have a thread angle. Okay, we have a unified English. You have refer table 10.1 from your textbook for metric. The list of board you can use for table 10.2. Also, we focus on the metric. How we select from this table the board, right? The board. Right, so this is table 10.1. This is in English. Table 10.1. This is chapter 10 in your textbook, Jovina. So this will be English. So you have all the size of the board, the major diameter, thread per inch. This one I mentioned when you have, remember just now I did mention earlier, when you have axial stress. Axial stress is sigma over force, tension, axial load of the board, not over the major diameter of the board. The area to area, this area. Tensile stress, sorry, I did say throat, tensile, my mistake, not throat. T means tensile stress area, because the board already have initial tension when we clamp it together. When then we apply axial force, we have axial force, we have 80. 80 is not true, my mistake. Tensile stress area, force over 10. We don't use the major diameter, actually, pi over 4 major. We already calculate, we have used from the table, right? That's one axial stress. Okay, this for English unit. All right, metric is table 10.2, right? It's the same thing. This one English, this one metric, right? Diameter of the board, the pitch, minor diameter, stress area, pitch, and so on, right? Okay, we have a coarse thread and fine thread. Coarse, I mean the distance between the pitch is much coarse. If you look coarse 0.5 pitch, means the board we have, board is a V shape, right? V shape. What is pitch? This one between the peak and the peak, right? The peak and the peak. Sorry, this 4-point line. Peak and the peak, that's a course. Kalau fine, they mean the pitch to more halus, right? So, okay. Okay, about the board strength. Actually, the board strength, normally when you do static analysis, we refer to SY, right? We refer to SY, but in board, because board have initial tension, so we use the proof strength. Proof strength of the board is a little bit lower than SY value when you plot stress over strain, because normally, for example, the axial stress acting on the board. All right, the proof load. So we use the proofs. We use the proof strength. We collected the board. We need to find the safety factor. The model static analysis safety factor and safety factor is SY over your sigma. For example, the board only have axial stress, right? Sigma axial. So you don't use SY. You use SP, proof strength, because the idea, because the board already have the initial. Okay, I did mention why this SY is much higher. Why would you use SP? Because proof strength, because the board have already initial tension when it is in connection, and it is jointed, it already have initial tension. Remember when you clamp with nut, right? When you clamp it, when you tighten it with nut, and it have already initial tension. That's why we don't use SY. It's even much lower. It even worsen it, because the board already have the initial tension. So then you apply axial load, you make it worse. So the strength is a little bit not SY. When you calculate safety factor of the board, and it's not SY, the denominator, SP over your stress that acting on the board. So be careful about SP. So what the value of FP you can get from table 10.4, right? Kelas, okay, kelas nampak kelas. I keep interrupting. Line, okay? Hello, class. Line, okay or not?
Okay.
All right, so this is also from your textbook. This is table 10.4. The table 10.1 talks about the size of the boat. This one, table 10.4, it means the strength of the boat, boat strength. So the boat, okay, the boat normally you will select what grade. Say you want to use grade 5 or you want to use grade 5.2. So you will refer what is the proof strength. Remember when you have axial load, you have to use proof strength. Remember this one. The other is English. Yeah, this one English, table 10.5 will be metric. So this is 85 KSI. Right? Okay, for metric, boat strength and this one. Okay, you want to use boat grade 5.8, for example. Even the better the grade, the lower the grade means the much higher quality the boat. The most lowest quality is grade 4.6. So it means the proof strength is 225. Right? Okay, remember the boat for the axial loading, you don't use the SY, you use the proof strength, right? Proof strength. Because why we don't use SY? Because the boat already have initial tension, right? And the proof strength is much lower than the yield strength, right? So it depends. You want to use higher quality grade bolt, you use 5.8. So this is a range of diameter for grade 4.6 and 10. This is a major diameter to M36. If you want to use, for example, M20 bolt, you can also go for what we call it. What we call this thing. You can go M20 bolt. You can also use grade 5.8. So main higher quality, they much expensive compared to grade. Right? So this is about 10.5 is about your boat strength. 10.4 is English. 10.5 is metric. All right. As I mentioned to you, we have type of loading. We have type of loading of the boat divided into primary load and also secondary load. Right? Okay. The primary load is a normal load, direct shear load. Okay. Normal load and direct shear load. Okay, later I will discuss, I'll show you what's the difference. The secondary load is a bending load and torsional load. All right, secondary load and torsional load. Okay, in this case, for you will not use this one. Remember when you use bending, bending is MC over I. You will not use MC over I. And also for the bending load, to calculate the F double prime. Let's say we will discover the torsional load. For torsional, we use TR over J. TR over J for this course. Later we discuss about it. So we have primary load and secondary load, right? Okay, for example, you have like this. So this direct axial load applied on the boat. Okay, the boat tightened by the nut at the bottom. So there is, if you look at the force direction, this is only axial load. So we have normal stress or axial stress equal to Fn prime. Prime means because that is a primary load. Okay? Primary load, F prime, V prime. Right? Kalau F double prime, V double prime, that is load due to bending or load due to short portion. That we will discuss for it. So this is a primary load, axial load. So Fn prime over area through area tensile. 80. Remember 80. We don't use major diameter. Plane A, we use 80. Where is 80? Can select, check from the table. All right, 10.2 for metric. Area tensile. All right, that is axial load. So we calculate the normal stress, axial stress, so the axial load over the area tensile of the boat. All right. Okay, this is a shear, direct shear. This is considered, okay, this one is primary load, this one is also primary load, direct shear. If you have a boat tightened by the nut, and then we have two plates joined together and we have this direction. So this is axial stress. So if we have axial, this is shear loading, direct shear stress. We have direct shear stress. Just now is axial stress or normal stress. This is direct shear stress, PNP. So we have, of course, we have what we call this thing, shear stress. We have shear loading, then we have shear stress. Shear stress, it means prime means this is a primary loading because shear and direct axial is a primary loading. And AR, okay, what is AR? It's not taking the, say, if I'm using M10, why is it area of shearing is 5/4, 10 square, right? So we don't use directly AR. So what is AR? AR is you can carry it from the table properties of for metric area of shear, right? Area of shear. You have area of shear. That's what you call area of AR. Yeah, but it depends. It depends. So, as mentioned to you, normally AR need depend. Kalau if you use M10, if on the shank, then you use M10. So it means here that you use diameter 10, right? Diameter 10. Depend on the. But if your area, the plane of shear is on the threaded part, then be careful about this. Why we call it AR. Area of shear to where is it? Area of shear. If it happen on the threaded part, see, we will take because the bolt is, sorry yang ini let me share dulu. Ini saya tak gemar mengajar. You can see my live video kan, kelas? Boleh nampak live video saya. Alright, kelas. So because this is what we have major diameter, minor diameter. So we have V shape. So this is major, right? Kalau you punya area of shear, plate of shearing happen between top plate, bottom plate, and we have shear loading. We have V like this. We have V like this. So if you're cutting off your shearing plane, okay, you have front plate and you have bottom plate. The area of shearing, the plane of shearing is on the threaded part, it's not on the shank. So you cannot take the major diameter. Clear tak logically? You will take the worst case, the minimum minor diameter. That's why AR2 means the worst case, the minor diameter. Right? Clear? Understand or not? To calculate the V over AR. But if when you have a plate, you have a bolt, okay, like this. But you punya area of shearing, some bolt, normally when you join two plate, this is the bottom plate, you join together. So normally the threaded part, most of the case, threaded only happen at here second. Here second, this is threaded part. I make it double line. So this is threaded. Normally, plate of shearing is on non-threaded. So this will be your major diameter of the bolt. If you use M10 bolt, it means 10 diameter because plate of shearing is not on it's on the shank, non-threaded, not on the threaded part. So this is your nut, right? So this is your bolt head. So it depends, depends on shearing to what is it. Because you have V here and you have V here. So torsional stress is V over area R where the plane of shearing. If plane on shearing is on the threaded part, be careful you take the minor diameter, not the major diameter, because both can we have major diameter and minor diameter. Even the minor, what is the minor diameter? You can check from the table, the minor diameter. Right? So that's means by. And let me share again the PowerPoint. Lain okay, boleh dengar saya kelas? Kelas boleh dengar? Lain okay? Kelas, lain okay ke?
Okay.
Alright, okay, this is a bending. Okay, this one tadi I direction stress. This is a primary load, normal stress, shear stress is primary loading. This is happen, this is secondary punya type of loading. Okay, when you look, for example, you have a bracket. You nampak my PowerPoint I'm sharing, right? Okay, you look at this diagram. We have a bracket, so this front view, this one is a side view. Okay, if the left one is a side view. We have a load, we have bracket, we mounted the bolt. We have when you apply the P is a loading, so it kind of like we have a bending stress. Bending stress for bolt is not like MC over I, like for example, like you have a shaft, right? Cantilever beam bending MC over I. The bolt, because it's a separate, it's not a homogeneous thing. It's a four bolt, for example. It's a separate thing. We don't calculate like MC over I. We calculate about when we have a bending. We apply load here, so mean we have kind of like have a pivot. It tends to pull out the bolt, due to the bending. So this is moment. This force P here produce moment at this X center point, pivot point. So due to the distance, this distance L, P over L is the moment. As you can see, P over L is produce moment. So the pivot is here because the bracket connected to this wall, or concrete wall. So we mounted the bolt at lower level and bolt at level 2, level 1, level 2. So it tends, due to moment, it tends to pull out the bolt. So it will produce a tension to the bolt. So this is a type of secondary loading, category secondary. loading applied to the board due to the moment. We try to pull out. So there's a question. So we will discuss on this later. Do not worry about this. We discuss on this. This due to moment. Secondary list of secondary offloading applied to the board. The next thing about secondary is about torsional. Torsional is like if you look on the cantilever beam here, you have this thing. Yeah, sometimes I just show you on live videos, much better to explain to you. Okay, if I share you my live, okay, you can see my live video for us. Okay, most of the, for example, like, okay, you have, for example, you have a beam. Are you watching my video, right? You have a vertical beam. Right, you are watching my live video, kan? Plus, you are watching my live video, boleh nampak?
Yes.
You have vertical beam. Okay, you have vertical beam. For example, you punya project lah, you have a structure. You don't have to design the structure. Actually, certain part until we discover. Okay, we have a beam. We have a cantilever beam like this. Okay, this is a horizontal beam connected to the standing leg of your machine. We have a C channel or what. Okay, this is vertical beam. This is horizontal cantilever beam. So you want to put a board. So we have a power board. So you design the arrangement, the board, the dimension here, for example, like you put that this one is 50 millimeter, 50 millimeter. This one, your design, 50 millimeter. You want to put the board A, board B, board C, board D. You design it like this. So you have a force. Let's say this is a weight from your motor or from your system, from all your shaft, your gear, and maybe your hopper, your feeder, and something, maybe your motor bracket, you want motor put on this. So let's say, for example, we have just a force here. We have a force F. Okay, this is a weight, right? So this is your bolt. So that's okay. This type of secondary loading, just now we show you bending. Okay, this is about torsional. When you have force here, okay, bolt, you don't select, okay, this one bolt I want to use M10, I want to use M7, M20. No, bolt you select everything the same. For example, I want to use M10 bolt. M10 bolt. I want to use M10. So I want to use M10 bolt. Okay, pitch later on, never mind. The main thing is about the major diameter M10. M stand for metric thread. 10 means the major diameter. It means the shank, the diameter. The major diameter of the thread. But major diameter, the peak and the peak, not the minor diameter. Minor diameter is the root and the root. The major or the shank diameter. M10. So you want to select either this M10 will fail on, will save or not. When you have a force, for example, you have 10 kilometers. Let's say this one is 10 kilometers. It's very heavy. Okay, 10 kilometers. You want to use M10. Okay, you design it 50. Okay, this is considered. If you look here, this is okay. When you design this A, B, C, D, so you must know the centroid. The first thing is the centroid because your arrangement of your board is a square shape. Sometimes it could be rectangular, sometimes it could be triangle shape, but this pattern of your board is a square shape. So the center, of course, of the center. So you know it is 25. 25 also from here to, I mean, CG is 25, right? Either from X and Y is 25. That is what you put in centroid. Okay. You put the centroid CG, yeah? After Peter called centroid is CG center. You put the center, lah. Okay, centroid is here. So this force, Guy, are you listening, class? Are you listening? Class, line, okay.
Yes.
For example, the direction, the force also you design from the centroid. You must know that for the force to the centroid, let's say I put it around. Let's say we put some value logically about 50, this is 50, 51, 200 millimeter. So everything is 200 millimeter unit. For force kilonewton. Okay. If you look, you have 4 boards, similar board, M10. So you have, when you look at it, look. So I draw the free body diagram, ABCD. So I focus on the board. Are you watching my video? So this is a board, I make a free body diagram, make it bigger. So it's a square shape. So we know that this is 50, and this is 50. Okay, this is your centroid. So this force applied on the board, it produces turning of the moment is what? this force on the center, because the boat we have configuration of force, so we need to find it, because this is a group of four. We need to find the centroid, right? At this, the distance from the centroid, this is your design, 200 millimeters. So it produces this turning of moment, right? Or we can call it torsion. Remember, torsion moment sama lah, torsion of moment. So like plus turning of clockwise, yeah. Are you listening? Turning of clockwise, right? Are you listening? Clockwise, right?
Yes.
But at the end here, the reaction is clockwise or counterclockwise of that moment. At the end, free body diagram. This is a fixed connector. So what the reaction? The reaction is counterclockwise. If I take the free body rate of the boat, betul tak? Plus counterclockwise is the same value but different direction. Betul tak? Plus, are you listening? Yeah, this one, you punya free body diagram, if you put the cantilever beam, you separate the cantilever beam. So this is the boat. Kan? So here is moment, right? If F time distance, betul tak? Boat is counterclockwise. You have to balance, right? So we focus on the boat. So it will be counterclockwise. But sometimes I explain to my student, remember you can make it same direction pun okay. Tapi this one is logically like that. It's depend how you make your decision. Clear, guys? Easy, Moment time. What is moment? Moment apa? What is moment just now? 10 kilonewton times 200. Times kilonewton. So moment is 10 kilonewton times 400 millimeter. Be careful about the unit, guys. So we have 2000 kilonewton millimeter or 2 kita ada 2000 kilonewton millimeter. Be careful about it. It's 2000 kilonewton millimeter. So this will be the moment. Or 2 times 10 to the power 6 Newton millimeter. Right? Okay, this will be your moment. But because since the reaction of the wall will be counter-react, turning counterclockwise direction, that's the value of your moment. But if you look here, this one is explained on the secondary forces. Right. Okay, if you look, this is a boat A, this is a boat B, boat C, and boat D, right? Okay, so this due to the torsion. We consider moment due to torsional. Moment is also top force turning distance torsional, because the total torsion, all right, the total torsional, right, all right, because we know that torsional is tau is TR over J, right? TR over J. Okay, due to, if you look here, when you design 50-50, so this one will be, this is your centroid, CG is your centroid. So you have a radius from each bolt to the centroid. So this will be the RA. This one will be the radius B. This one will be the radius C. This one will be the radius D. Okay, you design it because you know 50-50, you can, theorem Pythagoras, of course, you know 25 square, you know the radius. Of course, you know the radius. 150 because centroid here is 25, so you know the radius by this triangle, right? You know the radius. So the idea is that because the turning of moment or turning of the top is counterclockwise at the end of the boat, because when you look at the overall equilibrium is turning clockwise, but at the end it's counter-react. What is the value if 2 times 10 to the power 6 Newton? That's of your total top. When you look at this, so this one, it means that, so if you look on this free body, so it means that the boat is, this one the radius, okay, so this boat B, boat C, so this is radius A, this B, radius C, radius D. So this you have centroid. So this one, you have this one here, F double prime A. Are you watching class? Okay, this is not F prime to mean what? Direct axial load or shear load. This one is considered due to torsion. Are you watching class? Line, okay.
Yes.
Okay,
Yes.
Okay, this one is perpendicular to the centroid. F double prime A. So this one, each boat have their own individual due to the counter-react of the torsional. That's why I say moment torsional or moment due to the counter-react of the moment. So it's used like this. F double prime B is radius. This is perpendicular to the centroid, perpendicular to the centroid, and this one turning perpendicular to the radius. F double prime C and radius. F double prime C, sorry, this CD, this one D, it is F double prime D. So each individual board have this F W because due to the torsion just now. Torsion is 2 times 10 to the power 6 Newton. Or just like a moment. Moment torsion is the same thing. Torsion because total torsion apply on this 4 board. This is equal board, similar board, same size. This is our configuration, right? 50, 50, 25, 25 here, we know because central 25, 25. Right? Just now we already got the value called the distance 200 because the value of total torque is for moment 2 times 10 to the power 6, right? So total is 2 times 10 to the power 6 Newton millimeter. Total torque. Total torque. Why do I make this counterclockwise? Because the reaction of here is must be. Since this one make it clockwise, at the end the free body diagram, this one is counterclockwise. Okay. So the reaction is counterclockwise. So this individual board FA times radius A at the centroid is the individual torque because radius time coordinate is cos tangent to the because it's centroid because our configuration is so FA total torque is 2 times 10 to the power Newton equal to FA equal to FA prime times RA plus FD prime. FD prime is due to the torsion individual times RB plus FC prime time radius D plus because this individual torque radius perpendicular distance from the centroid is FA is perpendicular 90 degrees. So you produce individual torque or moment from the centroid. F time distance torque. FA time radius A plus FC time radius C plus FD time radius D plus FB time radius. Add it all together is the total torque that we calculate 2 times 10 to the power 6. Right, 10 to the power 6. And FC and FD double prime. Double prime is due to this torsion, right? FD time D. So this total 2 times to the. All right. The idea is that for we need to find what is the value of this FA. What is the value of this FB? FAB since it is configuration centroid the same, so FA, FB, FC, FD is the same value. So what is that value? So to make it shortcut, you have a multiplying factor. Okay, if I share you again, that's the idea of it. If I share you, your segment PowerPoint. Kelas PowerPoint apa? Kelas.
Nampak.
Yes.
Okay, PowerPoint. So this okay, this idea. So we have this thing. Okay, due to torsion. So we have a U. So we have a U. So this one I've been explaining to you. All this together, but this one the diagram is different that I showed to you just now. This is the same thing. You look at this note. So you have a U torsional distribution load. U is because due to summation. Total torque is U. So the idea of U is that perkali the distribution load. So U is the V double prime. So V double prime is UT times the radius. UT times the radius. So what is UT? UT is P1 over R1, P2 over R2. So this is what we call the U. So this is what we call the U. It's equal. So in this case, you punya U is total torque over you punya total moment over Alright. So this is a U value. Okay, this one you punya distribution load. So you punya total moment. Okay, if you look at the equation, this is important. This one. You look at this one. U is total. T is top. T is top. R1 square, R2 square, R3 square. So it means U punya U. I share you my video again. Okay, so see my live video. So it means that is F in my case here, FA times RA plus RB times RB plus RC, FA times RA, F double prime B times RB, F double prime C times RD, F double prime B times RD equal the total top multiplier times 10 to the power 6. So we need to U means. So the idea is that you need to find U mean is you punya total top or moment. I used to get moment or top somewhere. Do not confuse. I call momentary force. That is the moment over summation of Ri square. Ri square. So Ri, since in this case we have for Rn, Ra, Rc, Rd, we have since it's a square shape. So it means that you punya moment or top is now Ra square plus Rc, Rb square plus Rc square plus Rd square. So these are already the you punya apa tu? You punya perkali U. So the total moment. So first you need to find the U punya total distribution. So because why? You need to find what is the F double prime A, what is N prime A. Because since this is a square shape, all the radius is the same. All the radius you need to find the U. So U is for in our case. Okay, in our case, do not confuse. This is similar to top. I make more 2 times 10 to the power of 6. Okay, kilometer. So in this case, my U is. Are you watching a live video class?
Ada.
Right. So U tadi saya punya total moment tadi 2 times 10 to the power of 6 Newton millimeter atau 2000 kilonewton millimeter. Okay, let's say I put kilonewton millimeter. 2000 kilonewton millimeter. I still not convert to Newton meter and over Ri square. So just now my design tadi berapa? Jadi 50 again. 50. You are watching it, right? 50. So what is the radius? Radius what? Radius A, radius B, because this is a square shape. Even a rectangular shape also the same. Radius A, radius C, radius D, radius B is the same, right? So what is the radius? This is 25. 25. 25. So radius A equal to radius B equal to radius C equal to radius D equal to square root 25 square plus 25 square. Someone can you calculate for me square root of 25 cepat sikit kelas bantu saya. Kelas square root 25 square. We need to find the radius.
35.36.
0.36. Thank you. 5.36. So we need to find the U. So U means the formula of U is. So this U, right? Ri square. So it means Ra, Rb, Rc, Rd is the same. So in 2000 kilonewton millimeter over 35.36 square plus sama. Kita ada 4R lah kan? 4R square. Betul tak? Sama kan? 4R square. 4R, 4Ra, Rb, 4R square. So plus. Betul tak? So 2000 kilonewton millimeter over apa? 35.36. Berapa value of U? You need uniform. This the torsional distribution.
0.4.
0. Ini 4 4. Pasal kita ada U, Ra 35.36, Rb 35. All it is so for R square lah. 35.36 square times 4, 2000 km over ni. Berapa ni? 0.4.
4.
Betul Jangan salah kira, betul Kilonewton millimeter. Because di bawah ni millimeter square kan. So it means kilonewton per millimeter. Pasal dia so millimeter square atas millimeter cancel out sebawah 0.4 kilonewton per millimeter. Betul? Calculation 2000. Betul kelas?
Betul.
35.36 square times 4. Okay. 0.4 kilonewton per millimeter. So that point we need to find. So what is the FA? So what is FA? So FA, so you punya board tadi. Okay, you punya board just now. AB. Okay. Ni centroid. Okay, ni radius. It's a square shape. So ini FA. Because this is both A, this is both B. both C, and both D. So FA we have, we have FA double prime. This is secondary shear class, because this is acting shearing on the boat. Because boat is like this, right? It's a shearing. It's not axial load. It's not a tensor applied on the boat. It is second. FB also secondary. So FC secondary shear load. That's why secondary shear load. Hence FD double prime. So we know that it's 135.36, right? All the radius RA is 136. So what is the value of RA? What is the value of FA? So we need to find what is FA. So it means all the load is the same. What is FA? FA is, to get the FA, what is F to FA? F double prime is U times RB. Okay, U times RB. F double prime at B, that secondary shear load, they all perpendicular to the radius. Perpendicular to the radius. FB is U times RB. FC double prime is U times RC. FD double prime is U times RD. All equal because radius is the same. We already calculate the U. U is 0.4. U means the multiplication per unit length. Per unit length. So what will be the torsional secondary unit? Per unit length, 0.4 kilonewton per millimeter. So this equation, the total over total R squared. Okay. Because okay, this is the thing. So we need to find FA. So what is the value of the secondary shear load acting on both A? So FA double prime is U just now is U RA. So it means that 0.4 times so it means, okay, let me show you again. So it means that FA or FD, FC, FD is the same because radius is the same. Okay. So you mean FA double prime equal to FB double prime, FC double prime equal to FD double prime equal to U. This is same. Since radius is the same, so it's U times A. So for example, FA double prime equal to U times RA, because U is kilonewton per millimeter. Since we have the radius 35.36, so that will be the, because 0.5 kilonewton millimeter is per unit length, So the radius 35.36. Each radius is, all the radius is the same for CG. So F double prime A is U times the radius. So that will be total load. Direction of okay. So U is 0.4 kilonewton per millimeter. Radius A is 35.36 millimeter. So berapa value? Sama FA sama dengan FB sama berapa value? 0.4 times 35.36. Pas sikit lah. Are you watching?
14.14.
Yes.
14.14.
0.12 kilometers. So it means that, okay, watch me. In all perpendicular to the radius, perpendicular. So it is 14.12 unit is kilonewton, right? Okay, kilonewton. So same goes here, 14.12. So the vector is like the same magnitude, the same length. 14.12, this one also 14.12. So why do I make all this double prime? This is due to torsional secondary shearing. You know, your boat is like my pencil. Can you see my pencil? Boat is like this, right? Boat is like this. Not, bukan baring lah, bukan boat. Boat is like this. So all this FA double prime, FB double prime is kind of like cutting, shearing. It's not axial loading. This boat like you are pulling, that is axial load. That's why we go for bending. What is pulling out the boat. But this one is due to torsional just now, so it produce shearing. So F double prime due to torsional direction load. Tadi just now I didn't explain to you the direction load. Tadi we have direction. I show you yang direct torsional load 14.12 kilonewton. Each one of this sama lah kilonewton. This one also 14.12 kilonewton. The direction of vector is right of each boat, right? So you need to find U times the radius. That's all. U tadi be careful about formula. That shall we begin formula. It's in your notes. Pasal your selapan notes you kind like tell you that notes. MI RI square. This one M is the top. RI square of the dashboard. Right. Kelas, boleh bawa kelas, okey tak? Kelas. Telefon, boleh bawa tak kelas?
Okay.
Boleh tak?
Boleh.
Susah. Boleh. Saya pun rekod at opening line. Boleh kan? Susah tak susah. Ini yang saya terus jump to secondary. Actually kita primary shear load tadi ada. We have a primary shear load kan, direct downward. Pasal dia reaction on the board, dia balik, dia upward. Dan kita take the total shear pada the board. Itu saja board. Okay, tapi yang saya jump to secondary. This is secondary due to torsion. Sini you faham So you got FA, you got the value. You got the value. Each board yang tadi the vector is like this. You kena buat makan like dia vector. 14.1 arrangement is like this is secondary. This is shearing acting on the board. Okay, remember the board kita use M10 tadi. Nanti kita cari safety factor, right? M10. I mean the diameter of the board to later on to find this, right? Diameter of the board is 10, right? 10 millimeter of the board. Okay. So all this FA double prime, FD double prime, FC double prime, 14.12 kilonewton is a big secondary shear loading, shearing acting on the board. What about the primary? I skipped. The primary. So what about the primary? Primary shear load. I draw balik yang board. You have tadi board and you have board. You have vertical beam and you have cantilever horizontal beam. You're right. Tadi berapa saya cakap 10 kilonewton kan? Board A, board B, board C, board D. This is centroid. Right. This is centroid. Primary shear load kita dah jump straight to secondary. Just now I explain to you. Okay, kelas. Ada apa-apa berlaku ke? Kelas. Line okay?
Okay.
Dapat video saya full screen kan? Video. Boleh kan?
Betul.
Okay, tadi kita secondary shear loading. What about primary? After I go back, this is primary just now kan? Cantilever beam, I just make a rough report diagram. When you have beam tadi, draw again lah. Draw again. Tadi cakap you have beam, you have cantilever, this your vertical beam. Tadi lah, so you design. They all your design, 50, 50, 50, 50, right? So ni ada tadi load 10 kilonewton, right? Jarak daripada centroid. Centroid saya cakap 200 mm. Yang tadi 2000 kilonewton ada moment on top. Tapi primary shear, can you have 10 kilonewton? So it means because this is pre-board diagram at the other end, so it means at the board, primary shear kita dah skip tadi. That is the most important thing kita buat dulu. A, B, C, D, because this is the other end, this is centroid, the primary shear is B. Why is B? Saya nak testing juga. What is B apa? Dah tunjuk dah tu, berapa B? Direct shear. Berapa? Direct shear, primary shear, berapa?
10.
What is total B? On the four board. Four board is one group acting on the centroid. So what direction of V here?
10.
10 kilonewton lah.
Faham.
Pindah situ, group of four board together. All the four board carry direction load 10 kilonewton. Why do I make it upward? Why do I make it upward? Yeah, at the end direction is balance kan. This one is downward. What? Fixed joint. Upward. Tadi just now turning off moment or top clockwise. I mean counterclockwise. Clear? Plus ini. Counterclockwise kan. This one go upward. Faham guys? So kalau each four board ada direct primary shear load 10 kilonewton, tapi we have four board. So each board carry berapa? Kita ada four board. Divide by 4 lah. Betul tak guys? Are you watching or not class?
Yes.
Nah ini yang nama FA prime. Tadi double prime due to torsion. FB prime. Tapi normally saya letak V. Tak apalah, it's okay. Ini FA prime. Or primary. This is primary. Pasal kita have 4 equal boards. See, each board, the same side. Divide by 4. We have C prime, FD prime. So what is the value of that each both 10 kilonewton? So FA prime equal to FB prime, C prime equal to FB prime equal to total shear load 10 kilonewton bagi 4. Di berapa? 2.5 kilonewton. Faham tak kelas? Faham? Kan? From
Faham.
the direction, primary load. So each bolt have a direction. Can you say that vector is upward? Bolt B vector is upward, C is upward, 10 kilonewton. So the idea, we combine the vector based on the secondary shear load. Nampak tak? Same bolt A, B, C, D. Kita tambah, this one naik 2.5, 2.5. So we got the total vector of each bolt. Clear? Understand that? Pretty straightforward, right? So you combine it. So this is primary. You primary shear, right? Tadi secondary shear loading notion, primary shear. Combine the vector. So remember this one. We have this thing, right? You see this one. See, I draw on the same, Yang ini, where each one 2.5, right? Masuk agak sini. Saya nak kena draw balik. Tak payahlah saya masuk ke sini, Jadi A ni, dia pendek sikit, faham tak? Nampak ini, kalau you can see, ini 14 point, tapi this one perpendicular to the radius, 14. Ini vector ni, the magnitude ni, the length of the arrow ni macam proportionate to the magnitude, 14.2 lah. Ini upward. This one upward pendek sikit, pasal 2.5. Betul tak? 2.5 kilometer. 2.5 kilometer, 2.5 kilometer upward. This one also upward, pendek sikit. 2.5 kilometer. This one also ada upward 2.5 kilometer due to primary shear. Faham? Okey, saya lukis cantik sikit nanti korang tak nampak. Vektor tu saya lukis cantik. Boleh nampak live video kau tak nampak begitu. Okey. Kita ada bentuk square. Square. OA, OB, OC, OB. So yeah, so you punya radius. Okey, tadi kita ada radius kita tahu tadi 35 volt. Okey, yang ni kita ada 14.12. Okay, F double prime A 14.12. Di panjang. Dia ikut magnitude dia perpendicular to the radius. Dia ikut perpendicular to the radius. Kan boleh nampak video saya 14.12 F double prime.
Boleh.
Ini perpendicular to the radius, panjang sikit, ikut magnitude. 14.12 F double prime C. F double prime C, that one is the F double prime C perpendicular to the radius. 14 F double prime C 14.12. Ini yang secondary shear loading. The boat is like this. Tadi plus that kita merge the primary loading FA prime is apa tadi? 2.5, right? 2.5 kilometer. B also is upward, same total, same value. FD prime 2.5. I need upward, FD prime 2.5 kilometer. Ini upward. FC prime 2.5 kilometer upward. Okay, based on your logic, can you know you have to produce what is the worst? A, B, C, D. Kalau kita combine, you know vector kan? You belajar vector from class solid vector. I remember when you do reaction on the pairing vector, and total vector. Which board yang have longer vector? Tell me. All the board is the same size. Tapi which one yang critical? Have the longer vector of combined F prime and F double prime. Which one? Both A, B, C, D. Which one have longer vector? The primary all going upward, but the magnitude is 2.5. Class, I'm asking you, class. Which both have total longer vector? You boleh nampak tak drawing saya ni, kelas? Kapau ni tak faham lagi ke apa dia cakap? This no manipulate. Which vector longer? A, B, C, D. Total vector longer.
B and D.
Yeah, D and D. Betul tak? Why? Can you see? 2.5, 14.2. Longer vector. I make it R, total resultant, RB. You look at A. Why A is not critical? A, can you see? A, you see A. A is like this again. They have 2.5. Need to draw again. Why A is shorter? A, 9, 2.5. Then it goes here, 14.2. 14.2. Okay, 2.5, 14.2. So RA is here. Short. What? RC also the same short. C, look at C. C 9, 2.5, 9, 2.5, and here 14.2. 14.2. So, basta kita starting point dia kan, 2.5 naik, downward 14.2. Resultant ini RC, short. Okay, tengok C, B and D. B, tengok sini, B punya board, naik above 2.5 and 14.2, that direction. Vector. So, can you see this one? Starting here, 2.5, 14.2, vector R, D, longer. Same goes for D. Sama. D, both at D, 9, upward, 2.5, then vector 14.2. Class, are you watching? Class, line okay? Class? Hello, class. Line okay tak? Saya kena interact, nanti penat saya kat kelas. Line okay? Can you hear me? Ya. Terputus. Kelas?
Yes, yes.
Line okay?
I can hear.
Yeah, right. So, 2.5, 40.2, vector RRC, longer, same value, same as good. RPRP, we call this one 40. Nampak tak? B and C, longer vector. So, we take either B and D. Understand? So, you kena calculate lah theorem Pythagoras. Kalau bukan susah pun, you dah know mathematics, right? You already learn mathematics. For your engineer, you know how to calculate this. Otherwise, a vector, so calculate. Okay, I take B or D can be. Okay, I take D. Because B and D is a critical, longer vector. So B and D is critical, not A and C. So I ignore A and C. D and D. Let's say I focus on B. So B, the board is like this. So the B. So we have tadi 2.5 and at least 14.2. So what, macam mana kita, how do we calculate total vector? Of course, you tak tahu hukum cosine. Macam mana? Tengok kalau you tak show je. Tak boleh show. Board ni dia punya difficult on this part dia, teorem Pythagoras ya. Delicate. Itu je. Dia tak actually formula not difficult. Cuma pasal ni centroid kan. Ini board B. Board B. It is board B. Okay. You have tadi 35.36 is the radius from the CG. So you punya lady, B is 14.2. Okay, 14.2, value 14.2. And you have, are you watching guys my video? Ini vector
Yes.
2.5. So you geometry, theorem Pythagoras, hukum cosines. So you have value 2.5, 40.2. So this will be your total. Ini you have to calculate total resultant of the shearing load RB. We can't focus on both B and RB. It's both B, right? So how do we calculate this? How do we calculate? Apa angle? Angle ni berapa? We have tadi square shape kan? It's not rectangular kan? Square shape. Apa angle? 45 kan? 45 degree. So kita have triangle actually. We have triangle 2.5. We have 14.2, and we have this one, 2.5, 14.2. Apa RB ni? RD same, tapi I focus on one. Berapa angle? Theta ni berapa? Theta berapa? Berapa kelas? Cepat kelas. Berapa theta? Siapa bagi, saya bagi bonus point. Lagi bonus point PM. Cepatlah kelas. Give me theta. Cepat sikit. Siapa bagi, saya bagi bonus point. Bila sih. Theta ni macam ni. 45 degree.
135.
Yes, PM ni. Alright. Sorry class, that's the way I handle class. Saya nak participation. Sorry apa itu jangan cik hati, tapi it's okay, do not worry. PM ni. Okay, 135 Ada masalah nak cari ni? Tahu tak kenapa dia 135? Kenapa? Kenapa dia 135? 45 degree. Okay, so this is macam mana? This is perpendicular. It means from here, this radius to here is 90 degree. So you have 45. And here, the balance here is 45 kan? Ini balance, sorry, the 45. And this is 45. And this one is 90 degree. Balance is 45, right? So this is 45. And this one also 45, 45, 90. 35 degrees. Right? 135 degrees. So ini mathematical guys. Mathematical. Okay. So it means the theta here is 14.2. So what is the value? You know cosine rule? Cosine rule is cosine rule. How do you do cosine rule guys? Cosine rule macam mana? How do you get cosine? A plus hukum cosine macam mana?
A square plus B square minus 2AB cos theta.
Okay. I share you. You can see my live video kan? My live video maximum kan? Okay, ini. Okay, apa yang saya tadi? Kalau ini 2.5 40 betul. Okay, ini A, ini B, kan? B, triangle jadi, yang ni C, betul kan? C, ini theta, kan? Theta, apa? C equal to, apa tadi?
C square. C
equal. Okay, C square.
Equal to A square minus B square. A square plus.
A square plus B square.
Minus 2AB.
Minus 2AB.
Cos theta.
Betul kan? Itu arrangement saya CAB. Betul kan? C square equal A square plus B square minus 2AB cos theta. Clear? Hukum cosine. Cosine rules, right? Okay, so this is cosine rule. So here we have 2.5. So C square. So C square is RB. So RB A square is 2.5 square plus 2.5 square plus B is 14.2 square minus 2. A is 2.5. B is 14.2. Theta apa tadi? 135, right? Okay, ini RB square. So RB is C2 square root. So this one square root. Calculate for me. Boleh tak?
16.07.
RB equal to
16.07.
0.07. Okay. Alright. So it means RB is 0.67. So okay, we already calculate RB is 0.67. Yeah, good. All right, RB is zero. As mentioned to you, tadi the C and RB is the critical. So we take, for example, RB is the most longest vector. So RB is 0.67. So we made that. So okay, this RB is, okay, RB is, you calculate this thing, is 16.07. So it means the shear load at B, so it means like this. So if you look, the RB punya direction is like this, right? This direction, this direction. So it means this is bolt B. Kita focus on bolt B saja. Then we ignore all A, B, C. B and D. D is the same, but we focus on B, right? We ignore A and C. But we focus on B. B and D is the same, but focus on B. So it means we have a direction. We have a total like this. Okay, RB for the vector direction is like that. Vector direction. So RB is total is 16.07 kilonewton. Okay, if this is the case, this is 16.07. Okay, I want to, the bolt that I showed to you is M10. I want to use bolt. I mean the diameter. So the bolt to, I mean the shearing, I want to be at the shank, not the threaded part. I mean at the shank. So it means when I initially I made the cantilever beam. So it means that, so this is the beam. Just now I showed you at the beginning. The cantilever beam, we have 10 kilonewton. So this is a vertical beam. So you punya bolt is like this. So it means the beam, the cantilever beam and the vertical column here and the vertical channel, so plate and plate. So the joint, the bolt is not on the threaded part, is on the shank. So I just take the M10. You understand me? The diameter of the shank. Diameter of the shank. Okay, the total shear load, I think on the bolt B is 16.07. So this is a bolt is this, like my pencil, like this. So shear load, this direction, 16.07 kilonewton. So what type of stress happening? What type of stress? Sigma or tau? Plus, I'm asking you, 16.7 is total shear, is shear loading. So shear tau is total shear load, RB, over the area. Or AR, area of or area of your shear. So I'm using, because I'm focusing, it means that the cantilever beam, if I make a cross section, it means okay, this is part of bolt B, and this is vertical. Let's say the wall, the vertical channel is like this, like the plate and the plate. I show you the cross section, the plate and the plate. It means okay, this is the bolt head. Okay, the bolt head. Okay, this is the vertical channel. Punya tu, I'm focused on this. So this is your nut. Okay, so it means the shearing to only happen on the non-threaded part, only on the shank. The shearing, so this is the cantilever beam, this now. Cantilever beam. So the shearing of R2 not on the threaded part, on the shank, so even on the major diameter. So I just take the RB. So I take the diameter of the shank is major diameter 10. This major diameter 10. So it means, so diameter is 10. So RB is area of your bolt of the shank. So it means RB is 16.07 kilonewton. What is the diameter of the bolt? Pi over 4. Diameter of bolt is 10 square. Betul tak? Right? Because it's shear stress. 16.07 pi over 4, 10 square. Are you listening, class? All of you? Are you listening or not? Class?
Yes.
Okay, this is the total shear stress acting on the bolt. 16.07 kilonewton bagi pi over 4. Since the bolt I want to use M10. PCD the same size, but the worst case is D and D because the vector is longer on that. 16.7 kilonewton over pi over 4 10 square. Why are you using this? Because I'm using on the shank. I mean non-threaded part, major diameter. cross section of the board, pi over 4 of circle is like this, pi over 4 diameter square. So, berapa value? Okay, I need to make it as a megapascal. So 16.07 times 1000 over pi over 4 times square. Pasal this is, I want to make it Newton millimeter. So berapa value dia? It will be Newton millimeter square. So it will be in megapascal. Berapa? Pasal this one kilonewton. Berapa value guys in megapascal? Shear stress. Right, I'm waiting.
204.61.
2044.61 megapascal. Betul eh? Betul eh? Confirm? Megapascal Newton at time counter. Betul?
Betul.
Alright. Okay. So this is a shear stress. Alright. Shear stress. So I'm using bolt M10 just now. So this bolt is on bolt M10. So the safety factor. Okay. Safety factor. Because this is shear stress. This is not normal stress. This is not bending stress. This is shear stress. Do I use SY over tau or do I use SSY over tau? Which one do I use? Or to calculate the safety factor? This one is strength. This one shear strength. Which one do I use? This is shear strength. This is not sigma, guys. It's tau shear. Safety factor, shear strength over tau, not yield strength. Understand me? Shear strength over tau. Shear strength over tau. So what is SSY? SSY for distortion energy theory, remember SSY is 0.577 of your SY, right? 0.577 of your SY. So I need to know what is the SY value of my, it means the board. What is the properties of the board? So I need to know the SY value because safety factor is not actually my SY is tau. It is equal SSY over shear stress. Shear stress already got it to 4.61. So SSY is 0.577. So it means I need to know the yield strength value. So where is it? So in your textbook, let me share you again the. Let me share you again the. Let me share you again. Let me share you again the PowerPoint. Boleh nampak PowerPoint? Okay, you look on the table. Okay, kita use metric. So this one is metric. Okay, if you in your textbook table 10.4, are you watching PowerPoint guys? Table, it is usually from your textbook. Where are you watching?
Ada.
All right. From the table 10.5 is a metric. We are in metric, the bolt strength, bolt strength. So it means, okay, I want to use bolt M10, right? Tapi which grade? You have to decide which grade saya nak pakai. Which grade? If you look here, okay, let's say I want to use grade 5.8, better grade. You watching I want to use 5.8. Okay, 5.8. They have diameter from 5 to 24. M10 boleh pakai tak this one? I want to use grade 5.8. Diameter, this is major diameter, 5 to 24. M10, is it in this range? Yes. Betul? Class, are you watching? Okay.
Ada.
All right. Okay. Okay, let's say this one dia tak ada yield strength, dia tak ada yield strength. Never mind. Okay, if I want to use, for example, I don't want to use this one. Dia tak stated the yield strength. I don't know why. You can refer from the. You can refer from the apa? Okay, let's say I want to use grade. Okay, that one we have year strength 240. Okay. Okay, let's say I use the lowest grade. I want to check. Okay, grade 4.6, 5 to 36. So M10 is within the range. 5 through 36. So the year strength is 240. Okay, I want to check. I think this one will not pass because I'm using the lowest grade. Okay, look at SY is stated that I want to, okay, it means if you look on my left video again, okay, SY is 240. I want to use grade 4.6. Okay, 4.6. Share you that video today. All right, if you see my live video from the grade 4.6, SY 240, right? So SSY this now, SY 240 and SSY is 0.57. Ini DET, remember during static analysis, I already explained. SSY is 0.77, SY 0.577 of 240, berapa? Shear strength jadi berapa? That's 0.577 to 40 berapa?
Uh, 138.48.
138.48
48.
megapascal. So the shear strength. Safety factor is SSY over you punya total shear load, shear stress tadi. Shear stress kita calculate based on the longest vector yang tadi 16.7 to 04.61. So you mean selamat ke tak selamat? 138.48 over apa shear strength tadi? Shear strength 138.48, kita punya tau tadi berapa? 204.61. Is it safe or not? Your shear stress is bigger than your shear strength. Not safe. Faham tak? Faham tak, kelas? Kelas, are you with me? Are you listening? Do you understand what I'm talking about from the beginning? The rest of you. Faham tak? Okay, I want to use the lowest grade, 4.6. Can you see SY 240, shear strength 0.61, 138. So this is your shear strength, your safety factor 138, because our total shear strength is now is 244, even bigger than the strength. Of course, the boat will fail. So what do? I use the better grade, right? Or I use the, not 10, I use M, a boat yang bigger diameter. Clear or not? Do you understand? The bigger diameter. Okay, let's say I don't want to use, okay, if I want to use M10, okay, just to show you, I share you back the PowerPoint is now. Okay, if you look here, I cannot use 4.6. So it means if I take grade, okay, grade 5.8 is not showing the yield strength. Grade, I have to use both. If I want to use both M10, I have to use 8.8. Can you see 8.8? The yield strength is 660. All right, I say I want to use both. I want to still use both M10, but now I want to use better grade. I want to use better grade, which is because, okay, grade 8.8, my mistake. Grade 8.8, they don't have the 17. They only have 17 through 36. Apa that? 17 to they don't have 10. It means that the only way, since we don't have the yield strength, I don't know if you look on the table, they have it. Okay, so either the idea is that either I use the bigger diameter of both and make it bigger, M20, or if I still want to use both M10, I cannot use. If you look at the table, they don't have SY, so it means the only option I have, maybe on the textbook we have this thing. So it means I have to use grade 9.8. Why do I cannot use grade 8.8? Because grade 8.8, they only have diameter 70 to 36. 9.8, they have 1.6 to 16. So M10 is within the range. I can use M10. So it's about major diameter 1.6 to 16. So I can use M10 where they have grade 9.8 and okay, they don't have the yield strength. Okay, I will go for I will go for grade. If I still want to use this, the way I show some example equipment, because and I have to use 10.9. Okay, 10.9. So I have a yield strength of 940. Okay, I have a yield strength of 940, 10.9 still, because M10 6236, so M10 can be in this range. So the yield strength is 940. So I would change. So I would change to grade 10.9. See, if I want to use this a better quality, I can use M10, and the SY value is 940 megapascal. So it means that the yield strength, I'll share you back. I'll share you my video again. All right, if you look at my live video, so the grade 10.9, so I still want to use both M10 within the range. Grade 10.9 have the range of M10, SY is 940, SSY is 0.577 of 940, SSY jadi berapa? 0.577 940 jadi berapa? Plus 0.577 940 shear strength. 940 is SY. So what is the value?
542.38.
454.
542.38.
Apa? 5?
542.38.
5.2.38 megapascal. It will be shear strength, guys. Shear strength is 0.577. Remember this, your static analysis. EET, decision theory, SSY is 0.777. 5.2.38 megapascal shear strength. So it means that safety factor is the SSY over your total. Just now, tadi we calculate total shear strength vector, both and D vector is also D the same. Total vector 204. Total shear stress 16.07 is total vector RB. So shear stress 204.61. So 204.61, right? So tadi apa? S. Apa SY itu? 5.2.38 over 2. Ini selamatlah. Dapat 2 point something plus. Faham tak?
Faham.
Faham Itu cara you buat. You faham tak kelas?
Faham.
Okay, kita break sekejap pasal semalam tak ada kelas, break 10 minutes, 15 minutes. Boleh tak kita sambung balik untuk bending? Okay, boleh? Boleh kan?
Boleh.
Boleh kan? Kita direct solid lah. Direct solid. Buat focus. Break sekejap pasal kita start 10, 11, 12, 41 kan? Boleh tak? Break dalam 15 minit dan kita sambung balik sekejap, kita go for bending. Ini tercabut the boat, try to pull out boat. Tadi kita just based on shearing only. But there's another case due to bending. The other side, we have a distance. Not just on torsion, we have a bending also. All right. Okay, kita break for a while and I will see you 12 suku. All right. Okay, I'll stop here. I see you at 12:30. All right. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi. Class, can you hear me, class?
Yes.
Yes. All right, good. Okay, shall we continue? So tadi we stop at torsional stress, secondary shear stress, which is torsional, and we go another type of secondary loading or stress that happening is due to bending. All right. If I share you my you can see my live video, boleh? Right. Like, can you see my live video?
Yes.
Right. Okay. Another case due to bending. Due to bending, okay, let's go for a similar example that I explained to you just now. I explained to you ABCD, right? ABCD. Like this. So A, B, C, and D. We are using, actually I cakap M10. Actually M10 is quite small compared to 10. That's why when we use the lowest grade is now, when we go grade 4.6 is now. Tadi we just focus on this case. We have primary shear load and secondary shear load due to torsion. But the counterreact is at the end here is reverse. Shear load, and we have upward shear, direct shear load. So produce this top like this, and here it's counterclockwise. So we found out that the B is the largest vector. Then the torsional stress activator is direct as shear stress over total shear stress. Because B is the largest vector, maximum shear load on the vector, then calculate the shear stress due based on the diameter 10, and because shear plane to will occur on the shank, not on the threaded part. Be careful when on the threaded, if you design your boat on the threaded, not the shank, the thread, mean you don't take 10 as your cross-section diameter, you take the minor diameter. So M10, what is the minor diameter? You can look from the table. Minor diameter is have a value for M10. But I just show you, because I just show you just kind of like from two, I just make us as just immediate example like this. I just put M10. That's why grade 4.6 cannot do, then later just now kita go for grade. If I'm not mistaken, kita change to grade berapa grade? 9.8 for yang ada SY value grade 9.8 for what? On your textbook, also on your grade 8.8. Yeah, grade 8.8. We change to grade 8.8. Then we have the last one change to grade. Sorry, we change to grade 10.9. 10.9 upper grade for M10, because I'm using the just 10 millimeter compared to 10 kilonewton, kind of like, actually I will go for M20, for example. It's much easier. I can use, if I use M20, I can use grade 4.6 even, maybe M20. Let's say I use M20. Calculate your shear stress will be, if I'm using M20, shear stress will be lower. SSY for grade 4.6 is 0.5, so maybe it will be safe. That's how you calculate. Because since I'm using M10, small, quite small compared to 10 kilonewton, that's why I have to use grade 10.9, if I'm not mistaken. Grade, apa saya lupa, grade apa yang saya pakai tadi, grade higher grade, higher grade, I'm using grade, yeah, yang ada SY 10.9. For M10 grade. Okay, okay, if you look, the next case is, okay, let's see if you look on my, okay, this is basic like this. Okay, we have cantilever beam. What is we have this case? The same arrangement. Are you watching video there, class? Cepat sikit, kita nak aku satu. Kelas. Kelas video, okay? Hello, class. Line, okay. Can you see my live video?
Okay.
Class, can you hear me or not?
Yes, can see.
Yes.
Okay.
Okay. Right, good. Okay. What if, like this, we have the same cantilever beam. I make like this, and so we have I make a isometric view. So this for cantilever beam, we have this case. In the cantilever beam, to is more like L bar. This is an isometric view. You understand what I'm talking about? So this will be the vertical beam. Vertical beam can be box section. This is leg of your machine structure, and this is a cantilever beam like this. It's more like L shape. So this is isometric view, but you understand my sketching. So the beam will be like this, right? So this L bar, you understand? So like this, right? And okay, we have normally we have most of the case we have I need to consider the thickness of just to show you the thickness, or I ignore the thickness. Sometimes if I put the thickness of the beam, for welding nanti, next topic kita ada thickness. For this one, I just okay. This is a LB. Just now kita just straight saja, but this one we have okay like this. So this will your tadi just flat, so it means flat. Tadi it means like this. Tadi it means like this. You punya your vertical beam, okay, and you punya cantilever bar just like that saja. Tadi just macam tu saja. This isometric view, right? So you have both like that, right? So basically, so then your project engineer class, so you design structure. So you don't have to analyze structure to only certain part, maybe the bracket to hold the motor. Later we'll discuss about this for your minor project. You design bracket to hold the motor because your motor is heavy. You design the bracket, then you discuss with me in WhatsApp. So your board is this one is to apa tadi 10 km. Sorry, 10. No wonder saya tak selamat jadi sepatut 2 km I put 10 kan just now. Tak kan 10 km. Tak apa, never mind. 10 km memang tu is too big. Saya nak pakai pun boat M10. That's why yang grade 4.8. Kalau 2 km of course safe. I put it 10. Tak apalah, my mistake. We already calculate 10 km too big for boat M10. That's why I to use grade 9.8 is now higher grade for boat if I want to use M10. I hope you understand the way the approach tadi. There's a direct shear load and secondary shear load. But this one we have bending. Bending to not like this. This one we don't have bending. This kind like tadi, this not produce any kind like bending to the boat. It's kind like not pulling out the boat because it's only a direct shear load, secondary shear load, right? But what about this? Do you understand my sketching? Sama juga boat, sama juga 50 by 50. Do you understand my isometric sketching? Faham? We have an angle in this. And the same goes there. Berapa tadi 10 km like this. Yang tadi jarak dia from here, from centroid to here is, from here to here is, berapa tadi saya bagi 200, right? 200 mm. But let's say kita put some angle here. Let's say saya put 50 mm. Understand tak guys, this sketching? Do you understand me or not? Do you understand the sketching? The load is it. Guys, are you listening or not? This is the load of 10 km. Let's say you punya bracket like this. Class.
Yes.
Right, bagus. Okay, so the arrangement also 50-50 is the same. 50-50. Sama macam tadi. The same value of magnitude of the force. Tapi we shifted the offset 50 millimeter here. Okay, about the direct shear load tadi. Direct shear load, where we have direct, kalau we will look on the front view, if we look from here, the direct shear load and secondary shear load is not changing. It's the same what we already calculated, but plus that, we have, but when we look from this view, we have a 50 kilometer, the 10 kilometer is offsetted to here, 50 millimeter. So it means that, okay, look carefully. When I draw the side view, so this is a front isometric view. When I look from this right view, side view, right side view, so it means, look here, look carefully. You can look my watch. So yeah, okay, this is my vertical column, box section, and now my L beam to L bracket to dah become like this. Okay, so macam tu. Are you watching or not, class? Boleh nampak Okay, this is looking from this view. So now my load is here, 10 kilonewton, and the distance here is 50 mm. All right. Okay, this is just now the same arrangement about 50 by 50. Centroid is here. This is both A, both B, both C, both D. Right? A, B, C, D. When you're looking at the right side view, so this is the axis of your board. Axis of your board. This is we have both in line A, B. So it means A and B are there. The second level, C and D is there. Faham tak, class? This is the axis of the boat. Boat is this. Boat is like this. Betul tak, class? Boat is like this. Just now, tadi shear, boat is like this. Boat is like this. Boat is like that. Clear?
Clear.
Right. So, this 10 kilonewton times 50 is not producing the torsional just now, direction load. Can you see the boat is like this? What about if your force 10 kilonewton, what it will affect on the boat? Your boat is like that. This boat, A and B here, C and D there. You have 10 kilonewton pulling downward. It's kind of like to twist. It's kind of like to pull out the boat. Understand me? Let's say you have a pivot here. 10 kilonewton times at the pivot O. That will be your pivot. This 10 kilonewton, 10 millimeter, it produces kind of like turning off moment like this. Turning off moment like that. Betul tak? So it means it tends to pull out the boat A and B and tends to pull out the boat C and D. It giving a load. Pull out load, it means it's a tension load. It's not shear load. It's a tension load. Also C and D tension load. Okay. Logically, which boat have higher tension load? A or B or C? Let's say you have a moment 10 kilonewton times millimeter, that will be total moment, 10 kilonewton times 50. About this pivot, it produces 500 kilonewton millimeter moment. It tends to pull out A, B, and CD. Which one have highest tensile load? A, B, or CD? Which one have highest to pull out? That's what I'm talking about, class. I'm asking you. Nobody answering. AB, we have AB here, CD there. We have 10 kilonewton. Try to, because 10 kilonewton is this air bracket, right? This one. 10 kilonewton, we look from the right. This 10 kilonewton, due to this 10 kilonewton, look on the right side view is like this. It tends to pull out the boat because of this L bracket. This 10 kilonewton is. Which boat have higher tensile load? This is not about shearing. It's trying to pull out the boat. AB or CD?
AB.
Yeah, you are right. AB. AB is 10 because the pivot is at O, right? You try to pull out. Logically, AB is much higher tensile load compared to CD. So it's kind of like this. If I make if you zoom in a little bit, it's kind of like this. This is a pivot. I made a triangle. Macam tu. This one. Ini F tension at AB. FA and FB is the same, right? Dia punya magnitude macam ni. You see the length of this triangle. FC and D is about just only the distance. About FC and FD. FC tensile load on both C, tensile load on both D was only this long only. This length only. FA and B this length. Pasal pivot at this. So it means FA and FB have higher tensile load. It try to pull out because of this to 10 kilonewton, 10 millimeter. It tends to pull out the boat. To pull out the boat. You mean the boat is like this. Tension to pull out the boat. To pull out the boat. So this is about bending. Bending is not MC over I. I remember bending the shaft, and this is not nothing got to do about MC. It's about tensile load type due to moment of this bending tends to pull out the boat. So FA and FB is higher tensile load compared to FC and FD. Okay, how do, for example, just now we have uniform U just now for torsional load, right? U is total torque over Ri square, right? Summation of your Ri square. So here also you have a multiplying factor because how to get this FA? How to get the FA equal to FB? FC equal to FD. FC is not equal to FA because FC and FD is same load, but it's small tensile load compared if you look at the pivot. FA and B is the highest one, but it's equal. FA to equal to FB because A and B at the higher level. So you need to measure the length one here from the pivot L1 and also from the pivot to here length 2. You can see my sketching L1. So this one on your PowerPoint, but this is my version. This PowerPoint, they have kind of different version. Just read your PowerPoint notes. Okay, L1 and L2. So that's the equation. You need to get FA, FB, or FC, FD. You need to FA, to get FA, you need to know, because due to the length, for example, total moment, this produce 10 kilonewton times 50, 500 kilonewton meter. That is total moment produced to pull out. You mean FA times the L1 at pivot, FA times the distance, the pivot L1 plus FB times the distance, sorry, L1. L2 is the higher distance. FA times the high, this one, L2 is longer than L1. FA times L1 is for A tension. You mean FA times L1 plus FB times L1 plus FC times L, sorry, my mistake, FA times L2 berapa? FB times L2 plus FC times L1 plus kelas, boleh dengar line tak putus, kelas. FD times L1. Line okay.
Okay.
Alright. All this one, FA times L2 plus FB times, this is a pivot, it produces individual moment, right? Because total is 500 kilonewton meter, but FA times L1 individual moment to pull out moment plus FB also times L2, sorry, FA times L2, pivot L2, FB times L2 plus FC times L1, this one shorter, FD times L1, total, add it, total equal to the total moment, 500 kilonewton meter. So that's a, so we need to find what, that's the basic thing, but you need to find what is the value of that F, what is the pull-out tension force? What's that pull-out tension? So the basic formula, just shortcut explain to you, you have to find the U. So that just now torsional strength. The U is like this. You can, you are seeing my video. So you have to find U. You mean per unit length. Per unit length, U is your moment. Total moment is 500 kilonewton millimeter, 10 kilonewton times 50, okay, 500 kilonewton. What? Boleh dengar? Is it okay? Kelas?
Boleh dengar.
Boleh pasal ada bunyi tu saja. And summation of L I square. Take note on this. Take note on this formula. Take note on this formula. You can see my level N. So what is N? N is, okay, this level, how many bolt do you have? Are you watching class? First level, L1, at L2 level, how many bolt do you have at that level? Oh, you guys not listening, eh? How many bolt do I have at this level? N mean, how many bolt? This level, first level, how many bolt? I have bolt A and bolt B there, right? So 2. This level, we have 2 bolt. This level, we have 2 bolt because we have 4 bolt, right? N is, what is N? N is number of bolt on each level. Ni take note guys, ini on the PowerPoint slide different. Yeah, it's the same thing, but this is why I explain to you. Make sure you take note. N is number of bolt. It means each bolt, each level, we have 2 bolt, right? A, B there. Lower level, we have C, D. So it means 2. In this case, we have 2 bolt per level. Okay, and number one. And I is the distance from your pivot. Pivot is here, guys. Pivot is bottom there. So this one, this is L1 and L2, your design. You put the value. So what is L1? So it's not given. So it means that I would give you the dimension. Because, so what is L1? Let's say the thickness of the still not given. Since the bolt is 50. Let's say I give the 50 balance of I put this 10, 20. This is 10. I put some value, not 100, not too much, about 70, 20, 10. Okay, let's say it's about 70. I mean the thickness of this 70. Okay, 70. Logically, this 10 we have. Okay, we have 50. We have balance 10 already. Sky, I become it impromptu, I say what immediately. Example, we have 50, we have extra, put some value extra of from here to here, we have extra of 20, we have 20, 50, it means 50, 90. So it will be 90, cannot be. Sorry, let's say I put 80. 80 is the width. 80 is the width. So if this is 80, so what is the distance? What is L1 and L2? So L1 and L2 berapa? If the total width of this L is 80, so you can design the L1. L1 will be 15 kan? Try watching guys. L1 is 15 betul tak? 50. So yang ini L2 is, since the distance of here is 50, between AB and CD is 50, 15. This one L2 will be 15 plus 50. 15 plus 50 is 65. Are you watching class? Do you understand what I'm talking about? This one. Because I put the total thickness here is 80, so it means, so I know if this is 80, so if this is 80, the distance between these two both is 50, right? We have 80 means 15, 15. So the first level here, so the first level is 15. 15 L1, L2, because a pivot is here. Pivot is at this point, So 15 L. I hope you understand. It's basically your design. You design the length. L1 is 15, L2 is 65. All right. So you have to use U. So U moment and Li. That's Li. So it means that okay, Li square. So from N from I equal to 1. So mean I have two length, L1 and L2. So mean L1 square plus L2 square. Summation of it. L1 square plus L2 square. So it means I have here in this case my total moment. Okay, in this case my moment is 50 kilonewton 5 times 500. So my U is 50 kilonewton moment times 10 kilonewton times 500. That will be my total times 50 millimeter. Okay, so it will be 500 kilonewton meter over, so N, but what is my N? N is one level, N is number of bolt on each level. So it will be 2 summation of, this one summation of Li square. So it means that your L1 square plus L2 square. Okay, so it means L1 square plus L2 square. So it means my L1 is 15 square plus 65 square. So this will be your multiplication per unit length of tensile load. Can someone calculate this for me? If you are listening, can someone please calculate for me? So what will be my U in kilonewton per millimeter? So that's why I can know if FA, what is FA? Tensile load of here, U times L2, because FA is on L2. What is FA? U times L2. Can someone calculate for me what is the value of my U here?
0.0.
Okay, thank you very much. Okay. U is 0.05.
6.
0.06.
56.
0.056, right? 0.056 kilonewton. This is per unit length of tensile load. So this is a standard unit per unit length of tensile load. They actually the mathematical from this equation, total moment 500 kilonewton meter equal to FA times L2 FB times L2 plus FC times L1. So they make the equation is per unit length. So we have to use this is a basic formula. Take note, guys. This basic formula. Maybe slightly different than the PowerPoint. So this N is the number of bolt per Li square. So we only have L1 and L2. L1 square plus L2 square. Summation of this. Okay, 15 square plus 65 square. So we get the value U is 0.56. So if you want to know what is the value of FA and FB is equal because they are on the same level. They have the highest. If you look at the triangle, they have a more tensile load compared to FC. FC equal to FB. FA equal to FB. So I will focus on FA and FB. I will focus on FA. So I don't need to focus on FC, on FB since the tensile load is low. It's low, if load is low. FA is U times L2. A and B is on level 265. So it means FA equal to FB because they are in same level U times L2. Because FA and FB is L2, right? So that's a U. So it means U already we calculate is, so U is 0.056 kilonewton per millimeter. So L2, U design, L2 is 65. So L2 is 65. That's why because L1, FC, FD is on L1, 15 is low, tensile load is low. So that's why we use FA and FB case. FA equal to FB, U times L2. L2 is 65 millimeter. Can someone calculate at me? FA and FB have the same tensile load, which is much greater than FC and FD. So what is the value of FA and FB?
3.64.
3.64 kilonewton. Right? Please be careful about this is kilonewton. It's not meter, kilonewton. This is kilonewton. All right. This is kilonewton. I convert it to apa? Okay, this is kilonewton, right? This is kilonewton. Okay, if you look here, this is 3.64 kilometer. Remember that our previous just now, remember that when we do yang tadi, remember that yang tadi kita pada at boat B, we have total shear load due to direction as secondary shear and direction of the RB 16.07 kilonewton. That is at boat B. Again, remember this is boat A, boat B, boat C, boat D. But when we're looking at the right side view, we have this boat A, boat B, but boat B also have the same tensile load. A have a greater tensile load, the same as B because due to L2 distance. We is both. Just now from yang direction load, a secondary shear load, the worst case is both B and D at the bottom, but we focus at B. D also critical in terms of direction load, but the vector is like this, but this one like this. But when we look at this case, when we have offsetted a bracket like this, 10 kilonewton that I show you, 50 millimeter here, both A also, both A and B have the greater tensile load to pull out. So in this case, both A, B, C, D, which is the worst bolt, critical bolt, we need to focus. You understand me? In this case, both A and B greater tensile load. So it means total add together with this, which bolt yang the most critical, bolt B lah. Understand me? Bolt B lah, bolt B yang have, bolt B due to direct shear, secondary shear is because vector, right? Bolt D also the same. But bolt D, I'm not focused. Why bolt D not the worst case? Because due to bending, bolt D have lower tensile load. Bolt B still have the greater tensile load. So it means, so that tensile load acting on both B and A, 3.64. I don't need to calculate U times L1 for C and D because it's the lower tensile load. So I focus on the FA, FB. But FA, remember, both A, just now on our vector, just now, let me show you where's the vector diagram that I showed. Both A is not the total length of direct shear load and secondary shear load. Vector just now, right? We focus just now. We focus. Remember when we do the vector, when we do the vector that's based on this. Remember this diagram? The total, the length vector, both B have the total length. Both A for direct shear, secondary shear, it produce short, right? Here. For shearing, for secondary shear and primary shear due to direct shear and also torsional, both B have short vector. So we don't, both A have short vector. We don't focus on both A because both B have longer vector due to direct shear and secondary shear. And plus that, due to bending to pull out, both B also have the greater tensile load. So mean both B have is the worst case. So we need to focus only both B. Both B represent for both A, C and D because both B is the critical. So it means that okay, just now, boat B have 3.64 kilonewton. So when I draw like this, okay, you watch carefully. Guys, boleh look my video, okay? Sikit lagi nak habis. Boleh tak? Little bit I stand more because malam tak ada class. Class, are you watching?
Boleh, boleh.
Sikit little bit I stand a bit 10 minutes after one boleh tak? Sikit je, okay. When ini boat B, ini isometric view lah, isometric view. Boat B. But kita fokus boat B. Boat C just now I ignore. Boat A I don't know because boat A has greater tensile load as boat B to pull out, but in terms of shearing, direct shear, secondary shear, dia low vector, don't it? Okay, boat B yang the worst, direct shear, total vector of shearing, direct shear, secondary shear yang total RB tu dia maximum, and plus the tensile load image. Remember this one, we have that is now, we have ini boat B. Boat B is like this. This is a boat B. Okay, ini yang dia punya plane, plane yang dia put on the plane, this plane acting on it. So just now we have, remember that just now tadi we have mana tadi initially tadi kita total vector RB this 16.07 due to direct shear and secondary shear. This is vector at this angle. So I'm talking this isometric view. So you mean at this plane. Okay, this is a plane. Understand? This is a plane. So we have RB just now, RB, and kita already calculate. RB total vector is 16.07. I'm focusing on boat B. The boat is critical. Plus that, okay, you're watching. This is plane like this. This is on, okay, let's say this is X, this is Y. Okay, this is XY plane. XY plane. I'm talking about XY plane. On XY plane, we have RB vector 16 plus. Video okay tak? Little bit scale. Macam dia lagi. Okay? Plus video okay? Okay, little bit more. Okay, RB on XY plane vector, RB is 16.07. But when you look at the right, it times, okay, ini on Z. Where FA to 3.64. Tensile load, 3.64 kilonewton on the Z. It is Z, right? Okay, Z. We have tensile load, 3.64. We have shear load, 16.7. Remember shear load on here, we already calculated just now, right? Shear load, RB, we already have tau. Due to RB, this is shear load. We have already calculated tau just now on RB, just now is, berapa tadi saya pun dah. We just calculate tadi. Berapa total, okay, 204 yang tadi. Based on this RB, we have total shear stress on RB, because of this RB is 204. This one total 204.61. 0.61. We are going to calculate total shear stress based on direct shear, secondary shear RB. Okay, over the cross section pi over 4 and 10 pi over 4 10 square. So we got the total shear 204. But this is tensile load. Okay, ini supposed to be stress. Ini about load. So what is tensile stress? If I have, this is a tensile load, ini shearing, tensile load on Z direction. I have a tensile load. So what is the value of, what type of stress acting on that? FA ini producer. Before I put FA ini, we have tensile load FA. So we have a axial stress, right? We have sigma tensile, sigma tensile load, sigma axial, sigma normal, sigma N normal is tensile load. FA just now we calculate over. Okay, be careful about this thing. This one, if tensile load both is right, I don't use because I'm using M10. I'm not using cross sectional. This is tensile load. Tensile load we calculate FA is 3.64. I'm not using pi over 4 10 square. Be careful because remember both tensile load we use a tensile 80. So where is that 80? 80 is based on M10. If I share you again, let me share you the PowerPoint on the, even in your textbook. If in your textbook, if you look here, okay, in your textbook, you are watching my PowerPoint. Okay, table 10.1 just now. Table 10.1 for table 10.1 for M10. Are you looking class? Table 10.2. Are you looking at PowerPoint class? Are you listening or not?
Ada.
Okay, table 10.2, because nominal diameter, I'm using M10 Okay, for tensile load, because since FA, we calculate U times L2 3.64 kilonewton. I'm not using, because normal stress, axial load 3.64 over area cross section. I'm not using pi over 4 10 square, because tensile load, since when they are jointing together, they already have initial tension. We don't use for tensile load. Be careful about this. You have to remember this. Use AT. I'm not pi over 4 10 square. Use this one. Already calculate. Clear tak class? Area tensile. AT. 58 millimeter square. Okay. So take note about it. I'm using 50. I'm not using 10 over 4 10 square. No. Okay. For tensile load, I need to share you my. Okay, I hope you see my video balik. So I'm using 80, berapa tadi? 58. 58. Okay, from the table, from here, the table, 58.0 millimeter square. And the unit is millimeter. From table 10.2. So that is a tensile area from M10. Okay, for M10, the stress area. 80 is a tensile stress area. That is considered when you use 80. For tensile load, use 80. Do not use pi over 4 to scale. Do not use 10 millimeter cross section area. Already have 58 millimeter. So 58 millimeter. Are you watching? Eh? So tensile stress here. So tensile normal, sigma normal is FA just now is 3.64. Are you watching? Watching my video. 3.64 kilonewton kali 1000 pasal saya convert to Newton over 58 millimeter square. Can someone calculate for me this one? So I need to find this extent. We already have torsional stress 204 just now. The tensile load berapa? Be careful, ni 80 tau, area tensile lah, not pi over 4 square. 58 from the table. Okay, kalau sama calculate ni, 3.64 pasal ni kilonewton, I have to time 1000 to make Newton to make it megapascal. 58 millimeter square. So what is the value here? Cuba sikit kelas.
62.76.
62 ni dah kali 1000 Kan?
76.
Yeah. Okay, 0.76 megapascal. Right, so you mean normal stress here. This normal stress. Okay, this is shear stress 204.61. Normal stress is, this normal stress is 62.76 megapascal. So ni I draw balik. Last kali guys, sabar sikit. Okay, last kali. So this board B just now, this board B yang worst case lah. So dia badan dia macam ni. Okay, so this one yang ni kita pada this shank area lah, this plane. Okay, this is XY. Ini X, Y. This is Z. I hope you understand. Okay, on XY plane kita ada tadi shear stress. Kita ada here shear stress this direction. Tau is 204.61. Shear stress because of RB, that is now total vector RB 60.7 combined with direct shear, secondary shear, we have total vector. We have shear stress on this direction, shear stress, direct shear stress, total shear stress acting on XY plane 204.61 megapascal plus that we have normal stress, axial stress on the Z. This is on the Z. Normal stress pulling out of 62.76 megapascal. Okay, what is the total stress? We have sigma and we have tau. Remember DET? Remember DET? Remember this strategy? Sigma equivalent. When you have sigma and you have tau, so this both B is the most critical, have greater tensile load to pull out and also the greater vector of direct shear load and secondary shear load. We have shear stress plus the normal stress. So at this plane, can you see this direction? Can you see this plane yang angle plane? So di yang kita tak pakai. Alright. Okay, for this case. Okay, for this one, no, this was my mistake. Ignore this, my mistake. Ignore this. So for DET, for welding, then I think welding we go for next week. Okay, for this one, if you are listening, DET, sigma E, we have sigma and we have this, our element is somewhere around here at the shank area. So based on sigma E, DET theory, sigma equivalent is square root. If we have by-axis, right, sigma square plus 3 tau xy square. So tau xy tu is considered xy plane. This is tau. So this is tau. So your sigma, total sigma equivalent equal to sigma, this sigma is your normal stress. So square root 62.76 megapascal square plus, now 3 tau xy is your shear stress. Combined direct shear, secondary shear stress. This is considered tau xy on your element, right? Okay, on your element. So we have to, then 3 times 204.61 square. Can someone calculate me the sigma equivalent stress? Cepat sikit. Sikit lagi. Sorry guys. Sikit lagi. Kita nak habis. 2.76 square plus 3 to 4.61.
359.91.
359.91 megapascal. And this only mega. So these were our total equivalent stress based on DET, because bone is steel material accurate for DET, right? 359.91 megapascal. So this is our total stress. Okay, based on the, okay, if you, because sigma, remember DET, it convert the shear stress. DET, the shear stress and sigma, it convert to sigma, not sigma. Sigma means normal stress, bending stress. It's not shear stress, equivalent stress based on distortion energy theory. Sigma, if sigma we want to find this activator, it's no longer shear strength. It's no longer shear strength. It will be SY denominator. The denominator is not because sigma. Kalau just now tadi, my first example, I don't have shifted filament, all about shearing. Direct shear, secondary shear, that's why safety factor SSY, because we don't have any sigma. All is about torsional stress, tau. So safety factor SSY, shear strength, which is 0.577. SY over your total tau. Just now I already explained in the previous example. But this one continuation, we have shifted 50 millimeter, we have bending to pull it out. We have normal stress, we already calculate 62.76. But we need to calculate all together. Sigma square plus 3 tau s square. Okay, so we got the value 359. We got the value 359.91. So safety factor, okay, let's see, last one. Safety factor, either the bolt at B to safe or not. Safety factor, okay, remember for bolt, whatever about sigma, normal stress, what stress, sigma consider normal stress, we don't use SY, we will use SP. Be careful about this. Understand me, important, FT, SP, proof strength, because we are playing with that, we combine the shear and normal, we combine as a sigma. Kind of like when sigma, for bolt, this is only for bolt, you don't use SY, nominator will be proof strength, because bolt already have initial tension when it clamp to the nut is tightened. Initially, they have initial tension already. That's why you don't use SY, we use proof strength. So proof strength of the, just now we are using M10, right? Okay, so play around with table. Okay, just now, what is our denominator? Our sigma E. Okay, our sigma E. Sigma E is 359, that we calculate 359.91. So we have to look M10 balik. If I share you the notes that you are in your textbook on the escape class. Okay, you are watching my PowerPoint class? Hello, class. Class, last still hearing? Can you still hear me? Okay, class.
10.
Are you there? You can see my PowerPoint. Kita go for table bolt strength, table 10. We are not English. Metric. Tadi kita M10 kan. My calculation is just based on M10 kan. So it means that just now my sigma proof strength. Okay, proof strength mana dia? So what bolt that I want to use? Because I'm using M10, my sigma E is 359.91, right? That will be the, to calculate stability, that will be the denominator at the bottom. The denominator is proof strength. So which one will I use? Suggest me. That have range both M10. Which grade do I use? Are you watching table 10.5? Sigma E denominator, quantitative vector is SP, proof strength over sigma E. We have to use proof strength. So my sigma E is 359.91. So if, let's say, if I want to use grade 4.6, proof strength is 225. Cannot be lah, because my sigma E is already 359. Of course, my bolt will fail. If I want to use grade 4.8, it have from 1.6 to 60. I can use anything, but they don't have, okay, they have a proof strength 310. Can you see that one? Are you watching or not? Class table. Are you watching now? Table
Yes.
10.5. 310. 310 and 359 lower kan? Cannot, fail. 5.8, we have diameter from 5 to 24. Yes, both M10 can be there. 380. And 380, sigma E, our sigma E is 359. Yeah, safe lah. Tetapi safety factor kind like 1 point something. Am I right? 1.1. Not that safe. So we have to use, if I want to use bolt 8.8, what the diameter have 17 to 36. Tak boleh juga. So I have to use 9.8. Nampak tak kelas? Are you watching or not?
Nampak.
Then we use 9.8. This one 1.6 and 10 can be there. Proof strength. Remember proof strength 650. So I 9.8 guys. Share you. My live video balik. Okay, then nampak live video last kali guys. Taking your time. So and I'm using grade both M10, grade 9.8. That's my solution. So I have a proof strength. So safety factor proof strength 9.8 proof strength. Your speed is 650 megapascal. Okay. Table ni. Table 10 from your table 10.5. Okay. Table 10.5. Grade for M10, grade 9.8, proof strength 60. So safety factor is SP over your pencil saya pun dah habis tadi. Ya. Alamak, kejap. Saya pun dah habis. Panjang lebar saya bercerita. Okey. Pencil dah habis. Alright. SP over sigma E. SP 650. Sigma E tadi 359.91. Berapa guys? Selamatlah. Kelas.
1.8.
Selamatlah. 1.8 good enough lah. Jangan use yang tu. Faham tak guys? That's how you do board. Boleh guys? Boleh? That's how you do board. Boleh? Okay, that's all for today.
Boleh.
Sorry, taking the time. That's for board. Boleh? So nanti you design. You can either guys, you design, you select. My case, I already select board M10. There's another case. Both all your calculation in terms of variable diameter pun boleh. Itu kita discuss in the WhatsApp. It means you already set the safety factor, you want to with 2.5. You understand me? In design another approach, you will set the safety factor. Let's say you want safety factor 2.5 and all your calculation will be in variable diameter. Then you get the board, the closest board. Tapi the most simple way that I explain to you, you select the board and you check, play around with it. Kalau katakan M10, to my suggestion that if M10 is now calculate without the bending stress, without the pull out, already better I go for M15, M20 straight away calculate. Of course, if I use lower grade, like grade 5.8, grade 4.8, it can be safe, right? So this is okay. When in this case, for example, if I still want to use M10, I have to use grade 9.8. Because based on the total equivalent stress, based on the direct shear and also the tensile load, so we got the value there. So be careful. Proof strength for sigma, always proof strength. If I have only tau, no sigma, like for previous example, I don't have any pull-out load, direct shear load and secondary shear load, I have total tau, that one SSY over your tau. No, denominator is tau. Alright. So that's all about it. Okay, apa-apa you can ask me. Right? The proof factor. Okay. The class can you attend? Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Thank you, Doctor.
Okay.
Thank you, Doctor.
Okay.
Thank you, Doctor.
Okay.